Okay, dear students, now comes question number 4. The directional derivative of the function x squared yz squared in the direction of u I plus j plus k at 1 to 1 is blank. So here you need to recall the concept of this directional derivative. So let you see how I'm going to do this. So first we need to change the given non-zero unit vector to unit vector, and this is a vector given which is I plus j plus k. This is not a unit vector because its magnitude is radical 3, because square root of 1 square plus 1 square plus 1 square makes what? Radical 3, so it's not a unit. So to change a non-zero non-unit vector to unit vector, we need to divide the vector by its magnitude, as you know, and we need to have that one because it is a unit vector that has to be considered in our formula. So u is I plus j plus k, so we need to divide this by its normal, and this is 1 over radical 3 I plus j plus k now turns to be unit vector 4. And first next we need to determine the gradient of this function. So the gradient of this function is the partial derivative of f with respect to x along I, partial derivative of respect to I along j, and partial derivative of respect to z along k. So this is going to be this one. We just simply take the partial derivative with respect to x, which actually is 2xy z squared, as I wrote. And with respect to y, x squared with x squared z squared can come, and with respect to z, 2x squared yz can come, right? So these partial derivatives represents the gradient of the function. So now the next thing is we have to evaluate this gradient at the given point. So when you are taking x1, y2 and z1 here in place of fx, fy, fz, we can obtain this value to be 4i plus j plus 4k, as you see, right? 4i plus j plus 4k. So when we come to the meaning of this directional derivative of the function, it is the dot product of the gradient of the function at that particular point times, the dot with the unit vector, right? The unit vector u, as you see here. But we already determined what the gradient of f is. It is 4i plus j plus 4k. So unit vector u is 1 over radical 3 I plus j plus k. It's directly taken from this one. So this now can be done like this: 4 times 1 over radical 3 is 4 over radical 3, and 1 times 1 over radical 3 is 1 over radical 3, and 4 times 1 over radical 3 is going to come because this 1 over radical 3 is going to multiply each of these. And then, as can be shown, 4 over radical 3, 1 over radical 3 plus 4 over radical 3 is going to be obtained. So the slope of the tangent line you see to the surface in the direction of the given vector is going to be, at this particular point, is going to be 9 over radical 3. If you want, you can rationalize this. Otherwise, this can also be taken as it is. So when you rationalize this one, it will be 3 radical 3. So the directional derivative of the function at the particular point 1 to 1 in the direction of the given vector is going to be this much. Now comes the next question, and that is the fifth one, and it says you are asked to find the particular solution of this one. In fact, this is a second order non-homogeneous differential equations with constant coefficients. So here we need to find the homogeneous solutions and particular solution, and then we'll take the sum of the two finally. So the solution proceeds in this way. The characteristic equation for the homogeneous one is m squared minus 6m plus 8 equals 0, because as you see, just consider m to be in y, so m and the order of the derivative is considered as exponent here. So m squared minus 6m plus 8m the power of 0, because no derivative here, 8m the power of 0 is 8, is equal to 0 because now we are considering the homogeneous one. So from this, if you remember, this can be factored as m minus 4 and m minus 2, because we were thinking of two numbers where the sum is minus 6, product 8. Now from this, one can get m to be 4 or m to be 2. So the homogeneous solution is going to be c1 e to the power of 4t plus c2 times e to the power of 2t. Look here, student, that the homogeneous solution is having two constants, c1 and c2, and these are basically arbitrary constant numbers, real numbers. Okay, now we need to find the particular solution because this is not a homogeneous one, it's not zero, as you see. So we need to think of an expression where we can have this yp to be. So for that, look, this is written in terms of exponential form, so we need to take a here because this is a constant one, and e to the power of t because it's a coefficient of t1 is not the root for this homogeneous differential equation, but had it been a root we could have considered extra t in front, but for the time being let we take this to be a times e to the power of t. So the derivative of this is going to be a times e to the power of t. Again, the second derivative of this is this one. I'm taking yp to be in this form because you see I'm claiming here that the particular solution is of this kind. So yp's first prime and yp second derivative all are obtained, so I cannot directly put this second derivative result here in my equation and the first derivative result here also, and you see my yp to be here, so that I can adjust this in order to be q equal to 2 times e to the power of t. In doing so I can determine what is going to be. So this was, you see, my question I was having here. So just substituting the expressions here, I can have a times e to the power of t minus 6a e to the power of t minus 8a to the power of t. So this has to be equalized with 2 times e to the power of t because you have been told that this must make to e to the power of t. But I know that 1 minus 6 makes minus 5, and minus 5 with a minus 8 makes minus 13. So negative 13 times a e to the power of t equals to e to the power of t. So I can cancel now e to the power of t by e to the power of t. Now I'm left with a minus t over 13. So the value of a is now known. So if I am able to know what a is, I can directly substitute that here and know what my yp is. So my yp is going to be minus 2 over 13 times e to the power of t. So the particular solution is going to be the y homogeneous plus y particular. I mean, this is a general solution, students. This is a general solution. Actually, yeah, this says a particular, but make it general, students. General solution, okay? So the general solution is going to be the sum of the two. So c1 e to the power of 4t plus c2 e to the power of 2t minus t over 13 e to the power of t. So if you are asked to find the particular solution, in fact, you can put a to be negative 2 over 13 e to the power of t. It's possible to put that here. But if the question is, you see, to ask you a general solution, you are supposed to write this. But for the time being, even if I just have solved everything here, the question says a particular solution, so you are supposed to write this unknown, okay? Negative 2 over 13 is a power of t. Negative 2 over 13 is a power of t, but had it been a general solution, you see, we could have written this one. I hope you have understood it. Now, having this into account, what comes next is question number 6. This question says, find the value of k for which this given differential equation can be exact, right? So basically there is equal 0 here, students. Equal 0 here, it's forgotten, but we must have that one. So your m is x cubed y to the power of k, and your n is 1 over 2 yx to the power of 4. So the solution goes like this. Your m is x cubed y to the power of k, and from this the partial derivative of m with respect to y will be, as can be shown, this y to the power of k, when k comes down, it will be k x cubed y to the power of k minus 1. This is how the partial derivative of m with respect to y is going to be obtained. And your n of xy is the coefficient of dy, which actually is 1 over 2 yx to the power of 4. So your n of xy, as you see, is 1 over 2 yx to the power of 4. So the partial derivative of n with respect to x is nothing, but it is, you need to bring 4 down in 4 over 2, which actually is 2. Y is kept as it is, and deduct 1 from 4, you will have cube here, x cubed, so this is going to be 2x cubed y. But remember that a differential equation which actually is exact, must satisfy the condition that my equals nx. So my equals nx implied that, look, this is your my and this is your nx, so we can cancel x cubed by x cubed. In order to make it for general, x must be different from 0. So ky is a power of k minus 1 equals 2 times y can come. So the value of k can easily be directly obtained from this one. It is 2, and it agrees with all again these 2, because 2 minus 1 is 1. So even if it's not written, the exponent here is 1, 2. So the value of k is going to be 2, as you see. So for this differential equation to be exact, necessarily the value of k must be 2.